Who needs clouds? Come on. So this is a talk about how we, in our data center, use commodity hardware and an open source stack to get ourselves some awesome high availability goodness. My name is Paul Hinze, and this is Tony Pitluga. We're from Braintree. So what is Braintree? We help online businesses accept payments online. So we're a payment gateway. That means we're processing lots of awesome credit cards for a lot of awesome businesses. So let me just give you a quick overview of what our world looks like in our environment, because that'll help set the stage for some of this work that we're doing in our infrastructure. So a lot of people trust us with a core part of their business, their payments infrastructure. So the whole point of our business is that we're going to handle all of the credit card payments for your business so that you can focus on your core competency, whatever that may be. So all of these awesome companies, people like 37 Signals, Uber, and GitHub, are using us for all of their credit card processing. So what that looks like from the infrastructure side is we're seeing over 1 million API calls a day, which at a conference like this might be sort of a modest workload. But for us, every one of those is an incredibly important API call for our merchants. It's going to be something like a transaction or a credit card storage or maybe looking up an existing transaction. So to our merchants, every single API call is super important. So another way of putting that is downtime really sucks for us. If we're down, every one of our 1,000 merchants, or thousands of merchants, are unable to process payments, or in other words, unable to do business. So for us, downtime is like a higher order of failure. It's not just us. Not to complain, though, we have really interesting jobs. Being in an environment like this, where security and availability are of utmost importance, make being on the infrastructure team like we are, we basically have really hard problems to solve, and we can use some cool technology that we're going to show you today to do it.
So Paul did a really good job of framing kind of the business environment we work in, and I'm going to talk a little bit about the things that we value and how we make decisions. So we have like 3 big principles that we use: simple, not easy; open, not closed; and logic, not magic. So simple, not easy. I don't know who's seen the Rich Hickey talk from Strange Loop last year, where he talks about it's a
simple made easy.
But he talks about this a lot of, doing the easy thing is often quicker and easier. But the simple thing is more clear, more pure. It's going to be easier to understand in the end, and often the simple thing is much harder. So we always try to find the simplest solution to a problem, even if it's not the easiest. Open, not closed. Our stack from top to bottom is almost entirely open source. We believe in the open source community. We try to give back a lot to the open source community. We're going to go through a couple projects here that we've open sourced. And then logic, not magic. This might come from us being primarily Rails developers, and Rails has a lot of magic, a lot of metaprogramming, and you can kind of get lost in it. But if you really, dig in and understand the depths of Ruby, you can kind of understand all the stuff that they're doing, what's going on. So it's very important for us to know our stack the whole way down to the bottom. We can't depend on this Postgres query magically doing the right stuff. We need to understand how the query planner is going to work and understand how to tune things. Because if one of those transactions does not work, we can't just turn around and blame Postgres. It's all on us. So these values that we have kind of show the choices that we make. So standard, so some examples. So we chose Postgres instead of Oracle, Linux HA instead of an F5 load balancer. We use open source standards for encryption to store credit cards in our vault instead of a RSA tokenization device. In general, if we can build it ourselves or use an open source solution instead of buying a black box and shoving it into our data center, we choose that. Because we found that the open source solution, if shit hits the fan, we can figure out what went wrong. So today, we're going to be talking about our beloved load balancers. And to set a little bit more context, what is a load balancer? It's really performing 2 tasks, scalability and availability. So once you get to the point where one box can't handle all of the load that you need to do more than one box. So load balancer helps you spread the load around. It also provides availability because if one of the boxes in your pool is getting overloaded, the load balancer can take it out and serve your traffic with the remaining 2 boxes, remaining whatever boxes.
So a lot of the technology we're talking about today falls under the Linux HA umbrella. So that's high availability Linux, which is basically a suite of tools and technologies, kind of a loosely coupled suite of tools and technologies like most things in Linux are, that turn a Linux machine into a badass load balancer. So what you're going to see in a lot of these tools that we're showing you is that they follow the Unix philosophy, which can be sort of summed up as just do one thing well. And so what that means is you're going to see a lot of smaller tools interacting in using relatively simple protocols and sort of coming together to perform more complex tasks. The reason that I'm kind of setting the stage with that concept is I don't want you to panic because there's going to be a lot of small tools, and it can get kind of scary. This is my favorite slide. This is about where I stand here and just stare at it. It was really hard to prepare for this talk with a slide in here. You know, it can get really scary, right? Like when you see a lot of pieces interacting and you see something that seems to be incredibly complex as in aggregate. But the point is that these pieces are simple. That's what the Unix philosophy comes from, right? Each piece is independently understandable and, for us, really important, independently verifiable. So you layer these small, simple pieces together and you get more complex behaviors. And at the end of the day, your whole really becomes more than the sum of the parts because those parts are understandable, because those parts are simple. So let me give you I'm going to give you a quick overview of what we're going to talk about, and then we're going to talk about each technology individually. So here's the graph or the diagram that we'll keep coming back to. This is a basic request coming into our load balancer. So we just picked a merchant, say Uber. They run taxis. Let's say they're trying to post a transaction to us. That's just an HTTP call. Our load balancer is going to select a backend to process that transaction. It's going to hand the request off to Rails. And because of the way the networking is set up, it's an asymmetric network path. The backend node is going to respond directly to the merchant. So that's just a super high-level functional overview, and we're going to dive into a bunch of pieces of like what happens in this story. So there are 4 of them. One is IPVS, or IP Virtual Server. Also falls under this thing called Linux Virtual Server. That's the actual networking code that lives in kernel space that does the load balancing, the networking level load balancing on the box itself. 2 is a project called Litmus paper. It's a simple project that we open sourced. It's a status checker. It reports on the health of a backend node. 3 is a project called Big Brother. This is something in the space of ldirectd and keepalive D. It's going to query the health of the node and modify the IPVS state. And then 4 is Pacemaker to make sure that the load balancer itself is HA. So let's dive in. So like I said, IPVS, or IP Virtual Server, is a kernel space networking module that allows multiple backends to service traffic for a single IP. So it's in kernel space, so it's hella fast, and it's basically it's rolled into the stock Linux kernel now. So it only takes a couple of very simple steps to get it set up. So I'm actually going to show you those steps to kind of build up that diagram that we just saw. So you start with just a single IP tables rule to mark the traffic. The key parts of this rule here are the incoming IP address, the port, so we're just going to do HTTPS here, and then you set what's called a forward mark or a firewall mark. So we're going to just pick 7 here. This is what's going to mark the traffic for the IPVS subsystem to pick it up and decide where to route it. So then you use a tool called IPVS admin, or ADM, to create yourself a service for that firewall mark. So you see we're using the same 7 there. We're also picking a scheduler, which I'll talk about in a minute. That's the weighted least connection scheduler. And then we're going to add some backends to that service. So we're referencing that same firewall mark 7, and then we're making a real server, which is one of the backend nodes. We're using IP and IP encapsulation, so it's just going to wrap another IP packet around it and send it off. The backend node's going to de-encapsulate and get a packet just as if it were destined for the primary IP that we showed. So we're also giving it a weight. This will come in very important later. So let's give ourselves a second server here, 10.0.02. And now with those simple commands, we've built up the load balancer, the networking layer of that load balancer. And that's going to actually balance traffic across those two backend nodes. OK, so but what does that get us, really, right? So that gets us the scalability aspect, right? We're kind of distributing load across two nodes. But what about that availability part? That's where this weight comes in. So we can actually edit this weight at any time for whatever reason that we want. Because this weighted least connection scheduler is going to respect the weight and proportionally distribute the traffic out to backend nodes. So what that means is we have a ton of power. We can bring the weight down to 0 to perform maintenance. We can basically tune those weights to allow each service, each node, to best perform its service. So in an ideal situation, the weight is going to trend with the health of the node, where health is more or less the ability of that backend node to provide a given service. So the problem then becomes, how do we get health? And that's where Litmus paper comes in.
So Litmus paper is an open source project we have on GitHub. You can find it at Braintree/Litmus paper on GitHub. It's got a simple job of determining the health of a single node. So we want to take the concept of health and try to push it as far down the stack as we can. So for us, health means two things, dependencies and metrics. So it's easier just to go through an example of how we have all this set up. So this is a Litmus paper configuration file here, and it has two parts. The dependency is services that this node needs to have available to actually function. So we often do expose a heartbeat route in one of our applications to basically have it figure out all the things that it needs to be available. So if it needs access to a memcache or access to Redis or whatever, it's going to return only successful if all the things that it needs are available. And also, how healthy am I generally? So we use Factor to power these. So Factor is part of the Puppet suite that gives you a bunch of metrics off your box really, really easily. So these are kind of naive right now, just simple like CPU load, available memory. But what we really want to get out of this is if the box is getting overloaded, we want the weight to come down so the traffic can go other places. This is one place where I think we're going to iterate quite a bit of trying to find, like looking at queue sizes and looking at other metrics on the box that could give us a better sense of health, get into like some little laws stuff. So the other thing about, like we got this like crazy Ruby DSL to configure this thing, makes it really, really easy to extend. So let's say we're writing a Litmus paper for a postfix box, and Litmus paper doesn't support anything native to postfix out of the box. So you can simply write a Ruby file that has some checks in it and just throw require here. And since Ruby is dynamic, it's just going to pull the new file in, and you can use your new dependencies and new metrics. And it's easy as pie. So another feature that Litmus paper has that's really nice is it makes boxes easily discoverable. So if you are getting a Nagios alert of like, the disk is full on some box, you can SSH out there and curl localhost, and it'll tell you the service is running out there. And then you can dig in and see if this service is having a problem by just running another curl on localhost, and it'll break down the current state of the dependencies and the metrics. And Hinze mentioned being able to do maintenance, so we've written a small wrapper around Litmus, the REST API, called Litmus CTL, that gives you the easy ability to force the weight down to 0. So you say force down and then the service name, and it asks you for a reason. And then all queries the status after that will give you a 0. And then there's another command to basically remove the down file. But the reason is really important because if you're up at 4 a.m. doing something and this box is unhealthy, you can force it down, and then the next day you want to come in and pick it back up. You might not remember exactly what you did, but you can leave yourself a note. So we now have Litmus keeping tabs on all these backend nodes. Problem is, it just has the weight. We have no way to get the weight into IPVS. So Litmus will ask, answer who will ask. That's where Big Brother comes in. So Big Brother is another project we have out on GitHub. It has a simple job to monitor Litmus and update IPVS. It has a simple job. You could write this very, very simply of just a while loop that curls a Litmus, pulls the weight out of the HTTP response, and edits the IPVS server. We actually thought about doing this the first cut, but once you get a bunch of nodes, like having hot while loops, not a great thing. So we've written the thing in Event Machine, which is kind of like Node.js for Ruby. So it's responsible for querying all 70 nodes in our infrastructure and updating these things. And evented works really nice because it's just an HTTP call, and you can do a whole lot of that with very little CPU usage. So the config file, we didn't need the flexibility for Big Brother as we did for Litmus paper because we're not going to require Ruby classes to extend it. So we just did YAML. And you can see the main parts here is the checker interval, the scheduler, the forward mark. It's really all the stuff that we're going to pass down to IPVS. So Big Brother is really responsible for running all those IPVS commands that you saw Hinze go through earlier. So back to the big picture. Big Brother is now watching Litmus paper, updating the weights, and all is good. So this doesn't seem that big of a deal. Like why write this thing instead of using something off the shelf? There's an interesting thing you could run into with doing weight-based load balancing. So it's a really sharp tool that lets you distribute traffic around your data center really nicely, but it also has some sharp edges. And one of these is the thundering herd. So let's go through an example of that. So you got a bunch of boxes in your cluster that are all not doing too well. You got a big day and a lot of requests coming in. The health is pretty low, maybe your latency is going up. So what do you want to do? You want to put another box into the cluster to alleviate some of that pressure. So you put one in and it says, hey, nothing's running on me, my weight is 100. So now all of the traffic goes there because weighted least connection, the highest weight wins. So now instead of taking 25% of the traffic, it's taking 66% of the traffic. And ouch, yeah. So the worst case scenario is what's going to happen is it's going to oscillate of all the traffic is going to be taken off of this node and then put back onto it because the health is going to shoot right back up. So we've added this feature to Big Brother called ramp up time. So what we do is we will slowly ramp up the weight as you add in a new node. So you put the new node in and you get a 5 for your weight. So you see just a small amount of traffic go there, and then over time it will increase slowly until it gets to the weight that Litmus paper reports. So you'll see the weights. Eventually it'll normalize and things go much nicer when you put a new box in. So they all become healthy and the day is saved. So yeah, Big Brother's watching. Take it away.
And the remaining question then, so we have this nice system with Big Brother watching all the backend nodes, updating the IPVS stuff. So what if it goes down? There's all sorts of things that can go wrong on a single load balancer, right? Hardware failure, Big Brother can crash. It's perfect software because we wrote it, but it could crash. All sorts of mayhem could get cut loose. So you need something that will allow your load balancers to be highly available as well. So that's where Pacemaker comes in. Pacemaker has sort of a rocky reputation. Some people think of it as a scary monster that nobody really truly understands. There are crowds with pitchforks, but really it's a machine that will do exactly what you tell it to do. So that we could do a whole talk on Pacemaker, but I'm going to give you kind of an overview of how we use it. So basically, Pacemaker manages resources across a cluster. So a cluster being a collection of machines that can all perform the same role. So the important thing to talk about here is what is a concept of a resource from Pacemaker's perspective. That's where the Open Cluster Framework comes in, or OCF. I basically think of OCF as the init script standard for Pacemaker resources. Basically, it's just a standard for a script to accept a certain set of environment variables and arguments to start, stop, and monitor a given resource. So Big Brother comes with one of these. These are the three things that Pacemaker needs to be able to ensure that a resource is running on a given node in a cluster. Monitor is, are you running here? Start is, please start running here. And stop is, please stop running here. And Pacemaker has all sorts of rules and policy that you can apply to ensure that at least one node in your cluster, or however many nodes you need to, is running. So in our case, it's just one node. So Big Brother, we like these really simple, discoverable REST-based interfaces. So the OCF script that we wrote just has some very simple operations that it takes on the running instance of Big Brother. So the monitor is simply a GET to the given application that will return a Boolean, and the start is a put, and then the stop is a delete. So basically, from Big Brother's perspective, this is, so each of the three load balancers in our environment has the superset of configuration in Big Brother, but they all start not monitoring, and then Pacemaker will run starts on the appropriate nodes in the cluster. And from Big Brother's perspective, when it's running, when it's monitoring a cluster, it's doing those intervals, it's checking the configured Litmus paper nodes, and it's updating the weight in IPVS. So that's all well and good. We've got the IPVS tubes, basically, in the kernel getting set up by Big Brother. And then we need one more piece. So in our world, a resource up at the load balancer level is of one or more virtual IPs along with an IPVS cluster, because you need to be able to accept that traffic for the given service. So Pacemaker ships with a simple, a OCF script. I won't say simple, but it's simple in concept. So it's called ipattr2. Basically, so it's got start, stop, and monitor. That's basically running ipattr add, ipattr remove, and then it'll gratuitous ARP. So if your service migrates across, your new load balancer will pick up the IP. So let's show you how we configure this in Pacemaker. It's really simple. So you can see, coming from, you've seen interfaces that we've designed. You see the sort of interfaces that we like, really clean Ruby DSLs, really simple YAML files, and then you get to this. It's like, come on, guys. OK, so there's a lot here, but we'll kind of walk through the basic parts of it, and then I'll show you how we factor it up so we don't actually have to deal with this crazy XML. So first of all, there's a group around the outside. That's basically saying everything inside of this group needs to move together. So I said, right, there's two pieces to each conceptual resource for us. There's an IP, and there's a Big Brother. This is the Big Brother resource. So there's a lot of boilerplate here, and there's a lot of tunables for timings on how long the start, stop, and monitor should take. Generally, you sort of pick something that seems reasonable, and then you never think about it again until it breaks. But these values have been good for us so far. So really, when it all comes down to it, it comes down to these two lines. There's a provider, you tell it what the OCF script is, and then you pass whatever variables the OCF script expects to be able to identify the resource. So for Big Brother, it's just the name of the cluster. That's how it's going to set up those back-end curl requests to do the actual work. Similarly, here's a big block of XML that's like, similar, a lot of tunables, a lot of IDs that you have to make unique just because. But it all kind of boils down to, I'm going to use the ipattr2 script. I would like this IP address on this interface. So we hate this XML, and we never want to touch it. So what we've done is we lean on Puppet for this. So we use Puppet, the configuration management tool, which is really good at generating big configuration files that just need templates flipped in with variables. So when we factor this up to Puppet, it looks more like this. So we just have the concept of a Pacemaker IPVS resource. We give it the name, a nice description. There's the supervisor ID and the IP. And so we can have a list of IPs there, too, if we want to. If the service is available externally and internally, we'll have one external and one internal IP. So you can see, you can kind of distill it up to the things that actually matter for you. And you don't have to deal with that awful XML. So now we have Pacemaker running our load balancer. So Pacemaker's there. We have 3 load balancers. Pacemaker's ensuring that at least one load balancer is running all of our services. So this is not only true for our incoming primary gateway traffic, but this is also true of all of our internal services. Those all run through the load balancer in order to ensure that they're HA. So now we have all 3 pieces in place. We have Litmus paper reporting on the health. We have Big Brother checking the health and modifying IPVS. And we have Pacemaker in place to ensure that the load balancers themselves are HA. So this is kind of starting to look familiar. When you put it all together, it gets very complex. It's a lot of layers on top of each other. But we believe that simple open pieces that you can understand and verify individually really come together to make this system that is more powerful for it.
So just to recap, we have a lot of time left. Much faster than we thought we would. So today we went through what we value, how those values impact the decisions we make, and then kind of what we built and how we do business at Braintree. So again, Braintree, we have interesting jobs. Like everyone else here, we're hiring. So if you're looking for some cool stuff, come talk to us later. Any questions? Yeah. Here.
The question is, where does Pacemaker run? Yeah, use run in, and then I just repeat it. Just totally made it worthless.
So Pacemaker runs on each of the 3 load balancers. So Pacemaker is a quorum-based system, so you need at least 3 for it to be able to make good decisions. So it's running right on top of the things that you're managing.
Yeah, Pacemaker is actually a collection of tools that is running on all 3 nodes. It's using mostly it's like you give it a multicast interface, so it's broadcasting data, and it does stuff like quorum detection. It will determine like a master and a coordinator. There's all sorts of awesome stuff that Pacemaker does. So the answer to that question is very similar to like which of us is the conference. It's Pacemaker is running on the entire cluster.
So the question was, how long does it take us to fail over the VIPs? So Pacemaker will work on a 61-second polling interval. So if at least a minute is going to go past before or at most a minute will go past before it'll know that the system is down. Pretty much in the standard case, like the only reason we're going to move VIP on the load balancers is for maintenance or the entire load balancer crashes.
And in either of those cases, Pacemaker, if it's unable to get any data from a given node, it notices basically instantaneously. So the monitor command, like that 61-second monitor, is really only if a single service were to fail on your node. So basically, we ensure that all of the services are under TCP retransmission time, so that the effective answer to your question is no time, because TCP retransmission will just sort of cover over the whole of moving the VIP to another box. We're actually running this IPVS connection sync, which is like a tool as part of the IPVS suite that maintains TCP state across all 3 load balancers. So if you have an established connection on one load balancer and it fails, the other load balancer is going to know about that TCP session and just pick it up where it left off. Seamless.
So the question was, do we handle performance problems in the dependencies? Right now, it's really just an up-down. I think that's kind of the further work we want to do is to basically have the application expose how healthy it is and build like smarter tools to determine the health. So right now, it's pretty naive.
That was why we made it so extensible, because we knew that we would want to get smarter about this. We maybe want to look at packet queues or whatever is appropriate for the application. That's why those health, like everything is just a Ruby class. So if you can conceive of a way to convert your health into an integer, it's super easy to jam in some basic code and have it work throughout the entire system.
Saw this one.
So I love the idea of putting REST APIs
So the question was about ACLs. So being in the payment space, we have pretty severe ACLs about even getting into the production environment. So we haven't put anything in front of the REST endpoints, but to even get into there, you have to be like one of the chosen few. Does that answer your question?
Yes, we only let people who know what they're doing anywhere near these REST APIs, at least for now.
This one next.
Did you try any other bit failover systems before before Pacemaker? And if so, what were your experiences?
The question was, did we try any others before Pacemaker? And the answer is, neither of us did. We had another guy who had done a lot of the background discovery, and he was really familiar with Pacemaker, so we ended up with Pacemaker. Someone over here.
So with your PCI, everything has to be encrypted, when stored, and ACLs are great, but you really, a lot of people are using stateful firewalls to protect their environment. So you have an asymmetric path. So how's your security working in your environment?
So the question was, how is security working in the environment without a stateful firewall? You got anything?
Yeah, this is, you might be reaching the upper edge of the knowledge of us. So we're two developers coming on the infrastructure team. We have a couple of networking experts who are up at the top, at the very top layer, and we're just sort of starting to edge in on their bus factor. Yes,
Yeah,
everything is SSL. Hi. True.
So we haven't.
So the question is, why we said load balancing the load balancer. Really, we're just HAing the load balancers, which is true. I was just going for symmetry. So the question is, what are our plans for when a single load balancer can't handle its a significant proportion of the traffic? How do you actually scale across load balancers or balance across load balancers? And the answer to that question is we're not going to have to answer that question anytime soon. The current utilization on our load balancers, they're relatively modest boxes, and because the IPVS kernel space library is so damn fast, the utilization on the boxes are at a whisper right now. So I think that's a really interesting question, and I'm sure there are people who are thinking about that, but we won't have to in the near future.
So the question was, if one of the backends goes down, do clients notice? And the answer is yes. So it is just a polling system. So depending on how quickly we poll the requests, there will be some service that won't get there.
Yeah, so it's, we're by a standard we're using every 2 seconds. That's a tunable for us. So if we notice that we feel like the time to failure resolution is not good enough, that we'll definitely look into that. So that's the uncontrolled part. If during a controlled, like a Litmus ETL force down, the IPVS system, it will continue to route packets for existing TCP sessions. So for maintenance, what you'll see is just like a ramp down of traffic rather than just a cutoff.
So this is one of the things it's kind of difficult to tune because the heartbeats, they're not free. So you have to be cognizant of not heartbeating way too fast. And it's really a slider of like being able to react quickly to downtime and being able to actually handle your load and not generating too much artificial load from monitoring. So right now, the question was, how do you decide how fast to ramp things up because caches might be cold? The answer right now we have is we're not really load balancing anything with a cache yet. So everything that we're load balancing is just stateless HTTP things. So we don't really have to deal with that problem yet. Our databases are also controlled by Pacemaker, but it's not, that's like a whole other talk about how we do failover with that. So we really don't have to worry about that problem with the things that we've chosen to load balance.
It's a really interesting question though, and I think it's probably one we're going to have to come upon. I think the idea that we've started with is keep things really simple and keep them tunable. And then if you want to insert some intelligence later on, so if we want to insert a feature into Big Brother that actually interacts with the feedback mechanism to say, instead of just kind of guessing at an integer of seconds to ramp up, to actually say like, you tell me when to give you more traffic. That would be something that I would love to do in the future.
The question is, how are we measuring the effectiveness? Hasn't fallen over.
Yeah, monitoring. There's a big delta on where we'd like to be with monitoring and where we are. We're kind of in the process of building up a graphite infrastructure, graphite statsd infrastructure, but it's not at the point where we can. I would love to just have been showing you like graphs of like, here was it before this and here was it after. But really, we just have the after. We only have like more recent graphs. But we're trying to get better at it, and next year we'll have awesome graphs for you.
So I think the really important thing we want to measure is the relationship between the weight that Litmus paper is giving us and the actual health of the box, and trying to bring that delta down. And we just haven't gotten to actually getting really good measurements around that. Anything else? All right, thanks guys.
Yeah, thanks so much.
For your time.